Hello everyone, my name is Pratik Jadhav. So today now I am going to present my seminar on discriminant analysis. So firstly we have to see what is the discriminant analysis. So discriminant analysis is classify the objects belong from which population, and there are four types of discriminant analysis. So first is maximum likelihood discriminant rule, second is the likelihood ratio discriminant rule, third is a Fisher discriminant rule, and fourth is a Bayes discriminant rule. So now we have to see the probability of misclassification. So first of all, we have to see what is misclassification. Misclassification is the object is belong from the population 1, but it's classified into population 2. That is called the misclassification. So we have to see the probability of misclassification. So the methods of misclassification or discrimination have been discussed in the previous section. So, however, the important aspect of any classification procedure is the judgment of performance of the procedure. One way of judging this performance is to calculate the error rates or misclassification probability. So, we have to calculate the error rates in probability of misclassification. So, firstly, we get the ML discriminant rule states that the object with vector of values x is assigned to population 1 by 1 if likelihood of population 1 is greater than likelihood of population 2, where likelihood of ith population is the likelihood function of ith population, where Lix is the likelihood function of ith population, where I is equal to 1 comma 2. So if population 1 follows p-variate normal with mean vector mu1 and variance covariance matrix sigma, and population 2 follows p-variate normal with mean vector mu2 and variance covariance matrix sigma, then x is allocated to population 1 when mu1 minus mu2 dash sigma inverse x minus 1 by 2 mu1 minus mu2 dash sigma inverse mu1 plus mu2 greater than 0, then our object is belong from population 1, otherwise object is belong from population 2. So let us define a linear discriminant variable y such that y is equal to mu1 minus mu2 dash sigma inverse x. Assume that y is distributed normally, then mean of the y is equal to mu1 minus mu2 dash sigma inverse mu1, and the variance of y is equal to mu1 minus mu2 dash sigma inverse mu1 minus mu2 is equal to delta. So here x is assumed to be a member of population 1. Then the variance of y is the Mahalanobis distance for two multivariate normal population. Under this condition, the probability of misclassification of x is probability of y greater than equal to 1 by 2 mu1 minus mu2 dash sigma inverse mu1 minus mu2. So let us denote this probability by theta to 1, where theta to 1 is the probability of x is in population 2 given x is in population 1. That means the object is belong from the population 1, but it classified into population 2. So is equal to phi of minus 1 by 2 delta. So is equal to probability of y less than equal to 1 by 2 mu1 minus mu2 dash sigma inverse mu1 minus mu2. Here phi of dot is the cumulative distribution function of standard normal variate. Since the distribution is symmetric, so we can write the similar way theta 1 2 is equal to probability of x is in population 1 given x is in population 2. It means that the object is belong from population 2, but it's classified into population 1. So here is the form of the object 2 belong to population object belong from population 2, but it's classified into population 1 is equal to probability of y greater than equal to 1 by 2 mu1 minus mu2 dash sigma inverse mu1 minus mu2. So is equal to phi minus 1 by 2 delta, where theta 1 2 is the probability of misclassification of population 2 observation as population 1. Again, the discriminant function be d is equal to x dash su inverse x1 bar minus x2 bar minus 1 by 2 x1 bar plus x2 bar dash su inverse x bar 1 minus x2 bar. So the classification rule is the object is allocated from population 1 if discriminant function is greater than 0, otherwise belongs to population 2. So therefore the probability of misclassification is defined as theta 1 is equal to probability of d less than equal to 0, then object is belong from population 1 but is classified into population 2. So here is the form is equal to probability of x dash b minus mu dash 1 b divided by b dash sigma b in raised to half less than equal to 1 by 2 x1 bar plus x2 bar dash b minus mu 1 dash b divided by b dash sigma b raised to half. So is equal to phi of 1 by 2 x1 bar plus x2 bar dash b minus mu 1 dash b divided by b dash sigma b raised to half, where b is equal to SU inverse x1 bar minus x2 bar. Similarly, we have theta 2. So probability of x is in population 1 given x is in population 2. It means the object is belong from population 2 but is classified into population 1 is equal to phi of mu 1 mu 2 dash b minus 1 by 2 x1 bar plus x2 bar dash b divided by b dash sigma b raised to half. So Okamoto 1963 has discussed the method of finding the probabilities theta 1 and theta 2. Lechenbruch and Mickey 1968 also have discussed the procedure to find the value of theta 1 and theta 2 without discussing the complex distribution from of d. According to them, the dj values of jth unit of ith sample is given by. So here is the form of find the jth values of ith sample. So where Sj inverse is equal to n minus 3 divided by n minus 2 Su inverse plus Ci Su inverse xj minus xi bar xj minus xi bar dash Su inverse divided by 1 minus Ci of xj minus xj bar Su inverse xj minus xi bar. So n is equal to n1 plus n2 and Ci is equal to ni divided by ni minus 1 n minus 2. I is equal to 1 to dj can be calculated from the formula. This is the form of to calculate the dj after simplify. So now assign xj to population 1. Jth observation assigned to population 1 if discriminant function of jth unit is greater than 0. Otherwise, jth object belong from population 2. Then theta 1 and theta 2 are estimated by the proportion of misclassification. To estimate the theta 1 and theta 2, Luchenberg and Mickey have used another statistics. These are di bar is equal to 1 by n summation j from running to 1 to ni dij. Si square is equal to 1 divided by ni minus 1 summation j is equal to 1 to running from ni dij minus dj bar square, where I is equal to 1 and 2. Then theta 1 cap is equal to phi of minus d1 upon s1 and theta 2 cap is equal to phi of minus d2 upon s2, where phi of dot is the standardized normal distribution function. So another widely used method for error rate estimates is U method or cross validation. So Dillon and Goldstein 1984, which has been originally proposed by Luchenberger 1967. The method suggests to hold out one observation at a time to estimate the discriminant function for n1 plus n2 minus 1 observation. So then the classify the holdout observation by the derived discriminant function. The process of classification is repeated until all observations are classified by the above mentioned holdout process. So we have to remove the one observation and we have to find the discriminant function from remaining observations, and we have to done this for all observations. So let M1 and M2 be the member of sample objects misclassified in population 1 and population 2. So M1 is the misclassification of population 1 and M2 is the number of sample of misclassification population 2 respectively. Then the estimated classification error rates are given by theta 1 cap is equal to M1 upon N1 and theta 2 cap is equal to M2 by N2. So this method provides almost an unbiased estimator of theta 1 and theta 2. So here is the example. So let us estimate the probability of misclassification of an object in discriminating slugs M. rusticus and M. sowerby using the data. So first population is M. rusticus, length in millimeter and weight is gram. And for second population M. sowerby, length mm, weight gram. So here is our observations. So the data provided n1 is equal to n2 is equal to 20 observations. So we have 20 observations. So x1 bar mean for population 1 for length is equal to 47.500 and for weight is equal to 2.915. This is our S1. covariance matrix, and same as for x2 bar, mean for population 2, for length, for weight, and for second population covariance matrix, and SU is the overall covariance matrix. So for these two populations, the covariance matrix are homogeneous since NC inverse is equal to 0.71. So Boxham test with 3 degrees of freedom. For the data, the discriminant function is d is equal to minus 3.14286 plus 0.01598 x1 plus 0.94636 x2. x1 is for length, x2 is for weight. The discriminant score for sample objects for each populations are shown below. So here is our discriminant score for population 1. This is for population 1 and this is for population 2. So how we this calculate? So we have to just put the values of x1 and x2 in our discriminant function. So we will get this discriminant scores. We have to just put the x1 values for length and x2 for weight. Same for population 2. We have done it. So we will get the discriminant scores for population 1 and population 2. So from the above scores we have the mean discriminant score for population 1 is 0.375 and covariance matrix square is equal to 1.051. Same for discriminant score, mean discriminant score for population 2 and S2 square. Then theta 1 cap is equal to phi of minus d1 upon s1 is equal to phi of minus 0.36 and theta 2 cap is equal to phi of minus 0.39 where theta 1 cap is equal to 0.3594 and theta 2 cap is equal to 0.3483. So this shows the 35% of misclassification error. So there is another measures of performance of classification procedure which does not depend on the form of parent distribution or on the probability theory. This measure is called apparent error rate and is defined by the proportion of objects which are misclassified by the sample discriminant function. So let there be a N1 observations from population 1 and N2 observations from population 2 for a discriminant analysis. Consider that N1C object of population 1 and N2C objects of population 2 are correctly classified. So N1 and N2 are our observations, which means 20, and N1C our correct classified objects, and N2C is correct classified objects of population 2, and N1C are the correct classified objects from population 1. So then the classification table of objects is of the following form. So this is our following form. N1C our classified objects, N1 minus N1C is our misclassified objects, same as N2 minus N2C is our misclassified objects, N2C is our classified objects. So from using this form, we will calculate here the total number of misclassified objects are N1 plus N2 minus N1C minus N2C. So we will get the numbers of misclassified objects, and therefore apparent error rate is N1 plus N2 minus N1C minus N2C divided by N1 plus N2. We will get the apparent error rate. For our example, the classification table is obtained as follows. So we will get these values. So this is our classified values. This is our misclassified value. This is our misclassified value. This is our classified value. This is for population 2. This is for population 1. So therefore apparent error rate by using the upper formula. So this is our misclassified values addition. So 9 plus 8, 8 plus 9. This is our misclassified values. So adding these values divided by N1 plus N2, which means 40. So we will get the 0.425. Thus the 42.5% objects are misclassified by the sample discriminant function. The above process of measurement of performance can be used for any classification procedure. However, it tends to underestimate the actual error rate unless the sample size N1 and N2 are very large. So now probability of misclassification in several discrimination. The apparent error rate estimator discussed above is the most widely used estimator even when several groups are discriminated, though it suffers from a number of problems, especially in more than two group settings. For several group discrimination problems, a procedure to estimate misclassification error rate has been proposed by Fakunga and Kessler in 1973 and Glick 1978. The method is based on posterior probability and an object is assigned to a population having the largest posterior probability. So posterior probability means the objects after the belonging from population, then we'll calculate a probability, and prior probability where the object is not belonging from the population before probability. So let there be k populations and pi is the prior probability of an object belonging to ith population. I is equal to 1 to up to so k. Let f of x given I is the probability density of the vector of observations measured from the object from ith population. Then the posterior probability of ith population is given by. So here is the probability of objects belong from population I. Posterior probability is equal to pi f of x given I divided by f of x. Then the conditional density of x is f of x is equal to summation I running from 1 to k pi f of x given I. So from equation 1 we have k posterior probability. Let Ri Lynchburg 1975 be the ith set. I is equal to 1 to plus 1k of all values of x such that posterior probability of I given x is the largest among k posterior probabilities. Then the error rate for observation belonging to ith population is given by. So here is the ith population error rate. Theta I is equal to 1 minus integration Ri f of x given I. From equation 1 we have f of x given I is equal to prior probability inverse probability of posterior probability f of x by pi inverse probability of I given x f of x. So that theta is equal to 1 minus pi inverse integration pi given x f of x dx. So let us now define a random variable yij such that yij is equal to probability of I given x if xj belongs from Ri, otherwise 0. So now the right side of equation 2 is the expectation of yij where the expectation is taken with respect to f of x. Here j is equal to running 1 to n. Thus the posterior probability estimator of theta I is given by. So theta I cap is equal to 1 minus npi inverse summation j is running from 1 to n yij. From the definition of the random variable yij and from equation 2, it follows that expectation theta I cap is equal to theta I, so that theta I cap is an unbiased estimator of the error. The overall error rate estimator is the given point. So we have to find the overall error rate. So we have to use this formula. Theta cap is equal to summation I running from 1 to k p1 theta I cap. Since Ri is the region where posterior probability is the largest among all k posterior probabilities, one can use the definition of Ri to obtain theta cap, where theta cap is equal to 1 minus n inverse summation j is running from 1 to n, maximum of probability of 1 divided by xj, probability of 2 divided by xj, up to so on probability of k divided by xj. So we have to consider the maximum posterior probability. Here, the overall error rate estimator is the average of the maximum posterior probabilities for each observation, as I say. So here is test of discriminant function. So in discussing Fisher's linear discriminant function, it has been mentioned that there are R is equal to minimum of P comma K minus 1, where P is our variable, so linear composite, where R is the rank of within inverse and between sum of square. Within sum of square inverse to between sum of square. However, all these R composites may be significant or some of these may be significant. Only the significant composites are used to discriminate the groups. Bartlett 1947 has presented the method of test of the significance of the composites. So let pi1, pi2 up to so on pi r be the eigenvalues of within sum of square inverse into between sum of square. So Bartlett's proposed test is a method to test the significance of these R eigenvalues according to Bartlett. the test statistics. V is equal to V is our chi-square variate is equal to minus of n minus 1 minus 1 divided by 2 p plus k ln lambda. So where lambda is the Wilks lambda and is given by lambda is equal to product of j is equal to 1 to r 1 plus lambda j inverse r is equal to minimum p comma k minus 1. It's used to test the significance of the discriminant solution. Here v is the distributed as chi-square with p of k minus 1 degrees of freedom. The greater or equal values of p from a critical point of with p of k minus 1 degree of freedom leads to conclude that the discriminant solution is statistically significant. If the our chi-square value is significant, then we said that the our discriminant solution is statistically significant. It is seen that the statistic V has R additive components. Since the discriminant functions are uncorrelated, the additive components of V are each approximately distributed as chi-square variates, where the jth component has p plus k minus 2j degrees of freedom. Hence, the significance of jth eigenvalues can be assessed by computing the test statistics. So here is the form for calculate for each eigenvalues. So Vj is equal to n minus 1 minus 1 by 2 p plus k ln of 1 plus lambda j. These statistics help in deciding the number of statistical significant composites. The first j composites will be statistically significant if v minus v1 minus v2 minus up to so on minus vj minus 1 is greater than or equal to critical value of chi-square with p minus j plus 1 k minus j degrees of freedom. So what we have to done in this test of statistics. So our discriminant function is statistically significant. So we have to check our discriminant function is significantly classified our objects into two population. So here is the example. So it is seen that there are two eigenvalues of W inverse B for the data of example 8.5, and these are first eigenvalue and these are second eigenvalue. Let us investigate the significance of the discriminant solution, also the significance of the two composites. From the example, it is seen that n1 plus n1 is equal to n2 is equal to n3 is equal to 10. So there are three observations. P is equal to 2 and so n is equal to 30 and k is equal to groups are over 3. So now chi-square variate formula is equal to n minus 1 by 2 p plus k ln of 1 plus lambda j r is equal to 2. So the V is our distributed as chi-square variate with 4 degrees of freedom. Since probability of V is greater than equal to 0.38 greater than 0.05, the discriminant solution is not statistically significant. This implies that no discriminant function is statistically significant. It can be verified by observing the residual discrimination after partialing out of the jth component we have. So we have calculated for eigenvalue 1. First eigenvalue v1 is equal to n minus 1 by 2 p plus k ln of 1 plus lambda 1. So here is our probability 0.37 with 3 degrees of freedom, and for second eigenvalue is equal to 0.01 with 1 degrees of freedom. To investigate the significance of the first two discriminant functions, the test statistics is p minus v1 is equal to first eigenvalue minus second eigenvalue, so is equal to 0.01 with 1 degrees of freedom. The result indicates that the first two functions are not statistically significant. So we can say that the